It's a great pleasure to be here for a number of reasons. As Lado said, we've known each other a long time, much more than 30 years. It's also nice because I'm talking about superposing coherent states, and one of the influential papers on my work was by Vlado, along with Peter Knight, who is my PhD supervisor. There's another tie, and then the other one is a personal family tie. My daughter-in-law in Australia, she was a student at this university. So I'm not Slovak by blood, but I have Slovak family. So then it's nice to be here for family reasons, to see people. Okay, so what I'll tell you about now on superposing coherent states for fun and profit. So I'll tell you about coherent states, about superposing them, and we'll get the fun first, and then I'll finish by explaining how you can make money out of superposing coherent states. So that's the idea. I've got the affiliation Quantum City, which is on my clothing too, at the University of Calgary, and then I have some other ties up there. So I just finished 3 months at CERN, in particular being with the Open Quantum Institute, so trying to keep quantum technology open to the world, which is hard because people think it's a dangerous thing, and Vlado's on a committee with me with Open Quantum Institute. So I'm trying to fight the good fight to keep quantum open in a world where there's an attempt to close things. Okay, so superposing coherent states for fun and profit. I'll talk generally about it, and then towards the end, I'll get to some work I did. So there's a theory paper that came out a couple of years ago, robust macroscopic Schrödinger's cat on a nucleus. So I'm a theorist, but the experiments are done at the University of New South Wales in the group of Andrea Morello. So we developed a theory, and then the result, our experiment, we have more experimental stuff coming, but the experimental result based on that was published a year ago just over a year ago in Nature Physics, Schrödinger's cat states of a nuclear spin Qute in silicon. And that means that I'll talk about the coherent states and superposing, and then I'll move on to spin coherent states and superposing. So I'll work through kind of a historical perspective and what the field's about, and work to the point where I can then explain briefly our experiment and what we did. Okay, so first, just to give you some historical background, and then up here you can see 10/ and then some alphanumeric characters. So if you just type that into doi.org, a digital object identifier, it's just a short way of keeping track. The upper right paper is from Schrödinger's paper 100 years ago. So it's a centenary of that paper. And the upper left is related to Schrödinger. It's also Schrödinger. So on the right, Schrödinger introduced the Schrödinger equation, one way to solve quantum problems. And in his paper, this is written in German, his paper was written in German, the solution, if you solve the harmonic oscillator classically, you can think that there's a massive object that moves back and forth periodically. And then quantum mechanically, Schrödinger wrote the harmonic oscillator equation and solves it, and he gets a wave packet in position space. So that wave packet is a Gaussian, and the motion of the wave packet matches the classical motion. The width of it and its Fourier transform in momentum space, the product makes it a minimum uncertainty state. So it's the combined uncertainty in position and momentum is as small as it can get, and the width of the wave packet is time independent. And I'll explain in a moment that was the coherent state. So really the notion of the coherent state goes back 100 years to Schrödinger's solution, and there are three properties of that state that are important. Number one, it's the mean of the wave packet follows the classical oscillator motion. Number two, minimum uncertainty state. Number three, the width is constant, constant. Okay, so keep that notion in your mind. The second thing about Schrödinger is Schrödinger was one of a few that understood ramifications of quantum mechanics and was worried about it. He talked about the role of entanglement, and Einstein was also concerned. So he was in very good company. But the idea there is, he said, imagine the following problem. You have a cat, put the cat in a box, so the box is closed, you can't see the cat. Put in a nucleus undergoing radioactive decay, so an alpha particle decay. Then if you describe an alpha particle decay quantum mechanically, your alpha particle is a helium nucleus, 2 protons and 2 neutrons. You put it inside, and quantum mechanically, the alpha particle is in a box, but it can tunnel out. So in a nuclear model, you would say that your radioactive decay is in a superposition of not decaying and decaying. And the longer you wait, the higher the probability it decayed. So the higher the weighting of that. So quantum mechanics, even though you use a Geiger counter or some detector, and you hear click, 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 the quantum mechanical description doesn't tell you when the decay takes place. It says it's a superposition. Then you make a poison gas, and the poison gas, if there's a decay, it will trigger the poison gas to kill the cat. But quantum mechanics says the nuclear decay is in a superposition of decaying and not decaying, and a decay causes the gas to kill the cat, so you have an entangled state. You have undecayed nucleus, live cat, with decayed nucleus, dead cat, and then Schrödinger pointed out that an implication of quantum mechanics is even that the concept of life and death are no longer objective. So that was the way he posed it. Over time, with the Schrödinger cat, we now use the language where we would say, the cat is in a superposition of alive and dead, not what Schrödinger said. Schrödinger was entangled with the nuclear decay, but I'm going to talk about both ways. Just remember that Schrödinger's language, entangled with the nucleus, modern language, superposition of life and death. And then the superposition of life and death represents, mathematically, the way we use it now, is it's a superposition of 2 different states that are easily discernible, discriminatable, right? So if 2 states are not easy to tell apart, then it wouldn't count as cats. So that's the idea. Now, the coherent state story became called a coherent state in this paper, published in 1963 by Roy Glauber. And so this is the, so I've been working through it. There's a person in Japan, Yasunobu Nakamura. I was visiting Tokyo a few months ago, and he wrote a paper, he wrote an article for a Japanese magazine exploring coherence. So he talked to a lot of people saying, what is the first paper that uses the term coherence in quantum mechanics? And he and I helped out a bit, and others. So we now believe that's the first paper. So this paper by Glauber talks about coherence, published in 1963, and this is the paper that got Glauber his Nobel Prize in Physics. And so what he did, he was addressing an interesting problem. So in 1960, the first laser was invented. In fact, the first 6 lasers were invented in 6 months. So once Shavlov and Townes figured out the cavity, in 1960, 6 different versions of the laser were invented, but the theory was not very good. So it was nice. The experiments came out, theory wasn't good, and there was a very big debate between Glauber and Leonard Mandel, and the question was the following. If you shine a laser beam through a beam splitter, and you have photon detectors, will the statistics be independent, or will there be a bunching effect, or an anti-bunching, so an anti-correlation? Mandel argued for the anti-correlation. Glauber said no. And it comes down to a representation. Do you write your solution in terms of number states, so the number of photons? And that was standard in particle physics. And Glauber said no. What you should do, don't think about number of photons, go to this representation. So he's saying the electromagnetic field, the modes are just a collection of oscillators. Use that representation with Gaussian wave packets, and then if you shine light at a beam splitter, you'll see no correlation in the photon statistics. And that thinking is what got him a Nobel Prize. And you can see over here, his coherent state is just a Poissonian a Poissonian superposition of photon number. And he says, we shall call the alpha K, K is the different mode, coherent states. So he named Schrödinger's Gaussian wave packet a coherent state. So that's where the term coherent state comes from. We'll talk about if you take, I said like the oscillator goes like this, the superposition would be, imagine the oscillator in this state or this. And so the superposition of two coherent states is just the oscillator in a superposition of two motions that are just out of phase. Okay, so that's the idea of the coherent state. Then it's interesting going through. So first of all, so I've done digging and I try to find the very first superposition of coherent states. And now there was work before mathematically, Bionitzky, Birla, and various others and Titular and Glauber. So the papers went through using coherent states as a basis. But the first paper I can find that cleanly that talks about two coherent states in superposition came out of the Soviet Union, 1974, Dodonov, Malkin, and Manko. Dodonov is in Brazil now, and he had his 75th birthday celebration. I couldn't make it, I was online, but I did talk to him just to fact check. So I think I got my facts right. But I talked to him about the story of that paper. And so in that paper, they're thinking about a superposition of two coherent states, but they're thinking like mathematical physicists. So they write the paper, and you can see things like groups U11, UN1, and etc. And one thing that theoretical physicists don't like is mathematical physics, so the paper was not well read and not well cited. So it's the first one I can find, but then when you go to later work, it tends not to be a cited work. But historically, it's important. The next stage where the superposition comes up was by Jared Milburn when he was a postdoc at Imperial College. And so he didn't know, he wasn't looking for a superposition. But if you think about the oscillator, you can make an oscillator nonlinear, anharmonic oscillation, or you could say the oscillator is x squared plus p squared, and then you can add some small coefficient times the square of that. So Milburn was thinking about a particular nonlinear oscillator. The title of his paper says anharmonic oscillator, but anharmonic oscillator refers specifically to the cube of the position, and that's not what he did. So the anharmonic is not correct in the title, not used since, but he was interested in how to represent dynamics. So you write your equation, and then you want to represent the dynamics in a way that looks classical, so you get intuition. Historically, I don't have time to go into it, but it was very interesting. Dirac, in addressing the question, there was Schrödinger's equation and Heisenberg. Heisenberg used matrices, Schrödinger used differential equations. There was an argument in the 1920s, what was correct. Dirac realized they're both representations of the same thing, and then Dirac wrote about the commutators, but then Dirac had his own battle. There was another guy named Moyal, and Moyal was looking for representations of, find a new representation that matched the classical. So again, some history I don't have time to go into, but that whole concept of how you represent quantum dynamics so you can see how to think about classical has an interesting history. And that's what Milburn was interested in. How do I represent the dynamics of that nonlinear oscillator? And so when he did it, he's using a Wigner function. So the Wigner function is a way, in classical mechanics, we have a phase space, position, momentum, and we can represent the dynamics. So the harmonic oscillator in phase space would go like this. This axis is position, this is momentum. And so he wrote the equation. He didn't use the Wigner function, actually. He used the Q function, or you see me, I won't go into that. But he used some representation that was never negative and gave him intuition on the dynamics. And then his figure 8 in the paper, you can see here, there's 8a and b. And so 8b says after some time, that circle is a coherent state. It's the Gaussian in 2 dimensions. And the other circle is another coherent state. So figure 8b is showing in the physics literature the first superposition of two coherent states. And the figure 8a is a superposition of 4 coherent states. But he doesn't discuss it in the paper. He did it. He was my postdoc supervisor, so I've talked to him about it. He knew what he did, but it wasn't what his story was. It's interesting, figure 8b became a Physical Review Letters paper. So an entire PhysRev letter was written about 8b, and I'll show you that figure 8a became a Nature paper. So it's a rare case where you pull out 2 subfigures and each one became top papers on their own. And so what happened was Yerke and Stoller from AT&T Bell Labs saw the result. They found that very interesting. And then what they said is, and they talked to Milburn, they acknowledge him, and they say, we really like figure 8b, we're going to write about it. So they had to make things a bit different. So instead of just Hamiltonian, the energy plus the square of the energy, they said, what if it's not the square, it's the cube? So they played a bit with it, generalized the math a little bit, put in the decoherence terms, and showed, essentially elaborated on that, and said, how do you measure, how do you know you have that state? And the idea is that's a Wigner function in that green background. And then if you want to measure the position of momentum, optically homodyne detection, it's just marginal distributions. So your position distribution integrate over momentum, the vertical axis, the momentum distribution integrate over the position. And so they said, use the Wigner function, it tells you how to measure. So that was the early history. You can see 1974 mathematical physics, forgotten, and then it became physics work that came out. Now, experimentally, that as the cat state got to be understood, there were 2 experiments in the 1990s. One is the group of David Wineland, so that in Colorado, National Institute for Standards and Technology, and the one on the right is Serge Haroche's group at the École Normale Supérieure in Paris. And so the papers came out very similar times, and each one demonstrated cat states. Not great cat states, but they passed the bar. Interestingly enough, Wineland and Haroche, with the papers coming out, they both shared a Nobel Prize. There was a Nobel Prize that came out. Usually in physics there's 3, it was just 2. And so it's interesting I tell you this story, but the side-by-side papers were in the groups of 2 people who shared a Nobel Prize in physics for being able to control these microsystems and seeing effects. In Wineland's case, it's working with an ion, single ion, and then you can see over here, do you see equation 1? It's got ket happy face, ket up, ket sad face, ket down. And so this is the idea that you have a field that you treat, that's the oscillator. So one electromagnetic mode is an oscillator, and then the up or down refer to the internal state of an atom. So whether the ion is excited or ground. That's exactly what Schrödinger talked about with the Schrödinger's cat. So the up or down would be not decayed or decayed nucleus. So if up is not decayed, the happy face is the live cat, and the sad face is the dead cat. So that their experiment was demonstrating a realization of what Schrödinger talked about as an entanglement between the state of the ion and the state of the cat. And the cat being the field. It was the phonon mode, so it was the motion of the ion. So the ion is moving in a superposition like this. So that's what they do. Then if you measure the ion in the horizontal basis, so you measure your ion not whether its energy is up or down, but you use a technique. There's the Ramsey interferometer. Ramsey got a Nobel Prize in physics for this. And so I always say that because in my group with my students, I'm a tough supervisor. And so one of the requirements in my group is that my students need to know the Nobel Prizes in physics. So if there's a Nobel Prize in physics, they have no excuse for not knowing the physics. So it's just that way I carry on. So when I tell you that, it's me as a supervisor saying it, where I'm thinking, I know not everybody here is a physicist, but I always think it's good for physicists to know each Nobel Prize just for conversation. So that's why I keep saying it. Anyway, then if you measure with a Ramsey interferometry technique, then you can make a superposition of happy and sad, live and dead cat. And then over here, Serge Haroche worked differently. He would inject the atoms through the system, and this is a microwave cavity. And so in his case, it's Rydberg atoms, atoms with highly excited electron orbital going through, and so it's making a similar state to that. But instead of ions, it's neutral atoms. Instead of phonons or motion, it's the microwave field. So those were the experiments that got going. Okay, this developed further, so I'll just go through quickly on this slide to give you an idea, but there were various effects. This one, that's from Philippe Grangier's group, and so this one is Alexei Orjimtsov. He's now at École Normale Supérieure, and that was one where they showed what they called a kitten, and so the cat state is very different live and dead. The kitten state means there's, if you think of Gaussian, there's overlap between the two Gaussians. They did this by preparing a squeezed vacuum and subtracting a photon. So it's not a scalable way of making a cat. In English, we'll say if it walks like a duck and flies like a duck and quacks like a duck, it's a duck. So they used a technique where it's like a duck and it's not a duck. But that paper was quite important along the way. Meanwhile, in the group of Serge Haroche, he's tenacious. So you can see there a paper from 2008. In the Wigner function, you can see two Gaussian peaks, and you can see interference effects between. And the interference effects show you it's not a mixture of a cat alive and dead, it's a superposition. So the interference between the two peaks is important to know you're dealing with a quantum effect and not just a random thing where half the time the cat's alive and half dead. So Haroche was able to demonstrate solidly the interference effects. Okay, I mentioned that figure 8a became a Nature paper, so I'd put this in. I don't think Zurek knew about Milburn's work, but over here on the right, that picture from his Nature paper, those yellow disks are the coherent states, and you see 4 of them. He calls that a compass state, and the compass state it's a compass state because he's saying it's like on a map, north, south, east, west. Superposition of 4 coherent states, and he points out in his Nature paper that if you look between neighboring yellow, you can see the interference fringes in the Wigner function for phase space as ellipses. And so now the idea there, he talks about Planck scale. Planck scale is not the Planck scale of quantum cosmology here. Here, it's the area of the coherent state. So the area of the disk is the same for the vacuum state. So in the vacuum state, we talk about vacuum noise or shot noise. So for him, the Planck scale is the area of the coherent state circle. And then the ellipse has, in one dimension, it's narrower. So if you get those strips and they're narrower than the coherent state, that's what he calls sub-Planck. If you take a superposition of 2 coherent states, you can see interference fringes that are sub-Planck by his definition, but if you don't look the right direction, so you don't choose the right basis, you don't see it. So Zurek argued that if you consider the superposition of 4 coherent states, then you get what looks a little bit like a speckle pattern in the middle. So he found this to be very important because he's saying if you make a superposition of 4, no matter what measurement basis you use, you will see evidence of quantum superposition. And I won't go into it much except to say Zurek is interested in, the problem he's most interested in is if quantum mechanics holds in the early universe, can't we see effects of quantum mechanics from the early universe? And then the argument goes, and there's an area known as consistent histories in some people who do quantum mechanics that way. And so the idea is we do our astronomy and we don't see superposition. And Zurek is using that argument to talk about why we don't see superpositions. Okay, but that was related to Milburn's picture. And then, now, so we're still having fun. I'm going to get to the prophet soon. So I'm setting the stage. So this is still the fun part. Over here, there was a revolution that took place technically, and this is in the superconducting area, superconducting field. So Aroche's experiments were monumental. Being able to get these atoms to go through microwave cavities was really hard. And you can see it's hard because there are not many groups that try to reproduce what he did. It was monumentally difficult. But then in the superconducting area, so you make, basically superconductors are like conductors, but there's no resistance. And then you wind up with, you're able to make superpositions out of whether charge is on the left or the right of a Josephson junction. So some kind of barrier where electrons can tunnel through. And so building that system up, and this is the group of, Michel Devoret and Rob Schoelkopf. So the Nobel Prize last year went to Clark, Devoret, and Martinez. So Martinez was Clark's student. So the work came out of Martinez's PhD work, and then Devoret was separate. But between the three of them did work that first showed superposition on a macroscopic scale. And so Devoret, who's the second last author, just won a Nobel Prize for the superconducting system. And then Rob Schoelkopf and the group, there's Maziar Mirahimi, who's the theorist at INRIA or something in France, etc. A really good group. And so they, with the superconducting system, they can get a microwave field in a transmission line. They cut it off with and capacitively coupled to the rest of the line. But there's a microwave field essentially in one dimension in a cavity. And then here, they made a superposition of these coherent states. So over here, these are experimental results. And you can see in the upper left, that's 3 coherent states in superposition. And varying the parameters gives different types of interference effects. And this is the one that Milburn had, figure 8a, and the one that Zurich wrote about. And it's very funny. I've done some collaboration, not with them, but with Wallraff's group at ETH Zurich. And, I grew up in an era where, we thought of these things and nothing was ever something, you couldn't do anything. And nowadays, like in talking to these groups, and when I collaborated, say, well, you could do this. And they're saying, why? It's so straightforward. So if we're at an era where, you want some superposition of coherent states, you just tell them what you want and they make it, and they don't know why they don't even think it's interesting. Whereas for us earlier, it was like the dream to see it. So that was out of Schoelkopf's group, and they made that superposition of coherent states as the field in a microwave cavity. And you can see in this picture, this is the same group. These are 2 science papers 3 years apart. And then over here, you see that those are the microwave cavities there, those cylinders. And so they then said, if you can make a superposition of the oscillator, then imagine a second oscillator. That's what the 2 cavities are. But you do it like this. You have the oscillator in a superposition of this with the opposite. So that becomes an entangled state, right? So you just say, I don't want to make a superposition. I want to make 2 different modes in that. So if we go back to Schrödinger's cat, if Schrödinger's cat's a superposition of alive and dead, this is like saying I now have 2 cats, and I want a superposition where both are alive or both are dead. And so that's what's going on here. So they did that experiment and showed, I don't show the experimental results, but it's as clean as this, a little harder to visualize, but it's superposition with 1 mode, superposition with 2 modes. And then I come into the picture here, so you can see in the paper, they call it a Schrödinger's cat living in 2 boxes, but over here in the introduction, they say, alternatively, in the more natural eigenmode basis, has been known as the entangled coherent states in theoretical studies. So that was my term. So back in the early 90s, I started thinking about that issue and wrote about it in 2 modes and more modes, and I called it entangled coherent states. So it didn't get in the title, but at least somewhere they say, we're calling it this, but Barry Sanders called it that. So that's my claim to fame. And then this one, now I want to talk a little bit about that. There's really interesting stuff that comes in it. So I worked on and introduced the term entangled coherent states back in the early 90s. And then there was a workshop in Japan, 2010 or so, Osamu Hirota, and at Tamagawa University, and he asked me to be the opening speaker and give a talk about entangled coherent states. So I'm going to tell you what I found because it's interesting. So, of course, when I did it, I thought I was first. And then over time, you always discover you're not the first. So I'm the first at the name, but not the first at what was described. And so when I wrote the paper, tracing it back, so I kind of like history, I said here, entangled coherent state research since its first implicit use in 1967. The fact that it's 1967 is interesting, because I showed you the work that came out of Manko's group in Moscow in 1974 for one mode, and I'm saying here that the first case of two mode is 1967. So for some reason, the two mode version preceded the one mode version by 7 years. So let's understand why. And then here, oh, did I do it? Oh, sorry, I don't have it. I'm going to explain it, but I didn't put in the slide. So I'll just explain what happened. Okay, so is anybody here a particle physicist? Okay, so I'm going to pick on you guys. Okay, so this is the thing. So the paper in 1967 is about particle physics. So if I ask you, I'm going to ask you, can a particle be in a superposition of two different charges? So, you know, yes, no? No, okay. No, and there's no, yeah, no. Okay, they're both saying no. That's what the paper in 1967 is about. So let me just point out. So the paper, it's by Aharonov and Susskind, Yakir Aharonov, and Leonard Susskind. And they exactly go to this. So they write in the paper, that's the answer in particle physics. And there's the WWW, not the World Wide Web. It's the Wigner, Whiteman, I forgot the three W's. Wigner, Whiteman, and I forgot the third. 3 W's, one paper by two and another one by another. And so there's that theorem, and it's basically a super selection story. So quantum mechanics says, axiomatically, you can make a superposition of anything. But then in a particle physics world, the belief is you can't have a superposition of charges, you can't have like the quantum numbers that you write down to describe a particle can't be in superposition. And so they addressed the problem, and they said, the reason that people think you can't is it's something, nowadays we talk about quantum reference frames and quantum resource theories. So the idea is if you could get a particle in a superposition of charge and interfere it, then you could see the effect of a superposition of charge. And the way they do this mathematically is they say, consider a particle with a charge, but don't make the charge a fixed number, make it a Gaussian. So imagine that the electron charge is not 1e, but it's a Gaussian wave packet over charge. And then you say, can I have an electron in a superposition, or a particle in a superposition of positive or negative charge? In their description, it becomes a cat state, superposition of two Gaussians. And then if you want your charge to be exactly 1e, you squeeze it infinitely to get that fixed charge. And then they say, how would you do it? Then they say, consider two particles, the particle that you want to test and the reference. And when they do it, they have a particle and its reference as two Gaussians, and then they go through what the experiment would be to interfere. And so it's essentially a like if you say, well, if I have a particle and its reference both with positive charge and both with negative charge, that's the same as the two cats being in a superposition of alive and dead. So they say the reason in particle physics people don't accept it is because there's not a way of thinking about the reference. But the mathematics they did is the entangled coherent state. So that's my claim. That 1967, in addressing the charge superselection rule, they're saying there can't be a superselection rule. It's a forbidden resource that leads to it. So that's the 1967 work. Okay, then we go down to, okay, that's the end of the fun. And now we're on to profit. Okay, so now on the profit side, I'm going to explain why it's useful for quantum computing. and other things. And so this is work that came out of Yamamoto's group at Stanford University, Isaac Chuang, who with Nielsen wrote what we think of as the Bible of quantum computing, and Debbie Leung, she's a professor at University of Waterloo in mathematics now. And so they did some early work in error correction, and they said they considered how you would get around decoherence or loss. So your quantum system, your cat state, is very fragile to any kind of environment. And they said, we can get around some type of it by using what they called a bosonic quantum code. The term bosonic code is used a lot in quantum computing these days, in photonic and microwave quantum computing. After that, a better job was done on the code. And this is work that came out of University of Queensland. You can see Milburn's name again. There's Monroe and Paul Cochrane. And they said they introduced a code and essentially said, cat states. So your cat in a superposition of alive and dead. If there's a plus sign, it's logical 0. Minus sign, it's a logical 1. And they said, what if we did quantum computing where our bits, our 0s and 1s, are just superpositions of coherent states? And so then these guys developed, and then I was living in Australia, in Sydney, and they're good friends of mine. I said, hey, you guys, it's not complete. If you tell a 1 qubit story, it's not complete. You also need to do the 2 qubits. In order to set up a universal set of gates, you need to manipulate 1 quantum bit and manipulate 2. And so we then incorporated these entangled coherent states. We used the ion trap as a description, and then we had our story about codes. And then these are known nowadays as cat codes. And the cat codes include this entangled coherent state. But smarter people came along, and so this is Gottesman, Kitaev, and Preskill. And John Preskill is a leader of many things in quantum computing. And so the way I think about it is the cat can be alive or dead, but what if there were more states? You could be, alive or dead, or you could be really excited alive, or really, not quite dead, but a zombie. You can imagine different states. And so in their case, taking the cat idea, they're saying, well, let's consider not just superpose 2 Gaussians, but superpose more than 2 Gaussians. And remember what I said about the charge. If the charge is a Gaussian, and you make it infinitely narrow, then you have the fixed charge of an electron or something. So saying, let's take the limit where the Gaussian becomes infinitely thin, and the number of Gaussians goes to infinity. So mathematically, you have a problem that the limit making them thin and the limit of infinitely many don't commute. So it's mathematically incorrect, but insightful. And then that's what this represents. So they introduce a logical 0 state, and it's a superposition of infinitely many Gaussians, and each Gaussian is infinitely thin. And then this makes a comb, and in metrology, there's a notion of frequency combs which lock optical to microwave frequencies, and they're very important technologically. It's the same math. So the people working on coupling microwave to optical fields precisely use the same math as here. So comb is a good description. So you have your comb, superposition of Gaussians, and if you make another comb fit halfway between, that would be logical 1. So that's what they have. And then 1 and 0 are orthogonal because the Gaussians are infinitely thin, so the overlap of these two is 0. And then they say, in quantum computing, you have to say, I have 0 and 1, but I also want a superposition of 0 and 1. And then in that case, they say, take the Fourier transform. And so your comb, if its position in momentum, it's the Fourier transform of a comb is a comb, but the spacing of the teeth is inverted. So if the spacing goes as alpha, then the Fourier transform, it goes as 1 over alpha. So the Fourier transform of the comb is then a superposition of 0 and 1, and that's the plus state, and then the minus state is same thing. The Fourier transform, the dual, fits halfway between. So they introduced this as a way to think about how to represent zeros and ones. And then they're smart guys, and they said, okay, that's our thinking, but we know the math is really bad because two limits don't commute. And then they said, now let's consider realistically. And then there you can see the comb now has an envelope around it. And so there's a Gaussian around and Gaussian teeth of the comb. And then, of course, the Fourier transform would swap. It would take the width of the envelope and the width of the teeth swap. So they then deal with that. They're not clear in their paper, but the concept they conveyed is that it's not perfect and it should be taken care of with error correction. And I did talk to them. I talked to Dan Gottesman. I said, please tell me how you do quantum error correction. And he said that was Qute.sk. So I tried and I talked to Qute.sk and I couldn't get it. So each of them I approach and I say, why did you write that? And so they didn't deal with it, but each one points the finger at the other. But it's a great paper. I'm just joking around here. That's true what I said, but I'm not putting it down. And then they build up. I don't go through it, but there's circuits and all that stuff. And in a complicated story, they develop a theory of quantum computing using an infinite superposition of infinitely thin Gaussians, modify for the real world, argue it's correctable by error correction. But this particular model is actually part of business plans. So in Canada, two of the quantum computing companies, Xanadu in Toronto and Nord Quantique in Sherbrooke outside of Montreal, both are developing these systems, and other companies are too. So this story of superposing coherent states is relevant for quantum computing as a business. Okay, now I want to go to the spin case. So now I'm going to connect it with my own work. The harmonic oscillator, in physics, when you describe dynamics, there's symmetries to it. So the harmonic oscillator, the symmetry group is called the Heisenberg-Weyl group. Parelomov in 1971 wrote nilpotent group of Weyl. It's the same thing. So you say, okay, I know what the coherent state is for an oscillator. I know the Heisenberg-Weyl group applies. Can I then construct a coherent state for other symmetries? And the answer is yes. So what happened was the coherent state, I said, like that was 1963 by Glauber, an important notion and generalized. And then in 1970, there was a paper by Cortens, Arecki, Gilmore, and Clowder, and they considered atomic coherent states. So if you take an atom with the electron going around and you teach children about it, it's like a planet. But when you do the math of an atom, you have NLM, principal quantum number, angular momentum, etc. You can't see that orbit. But if you have a highly excited atom, your electron really goes around in an orbit. And if you want to describe that, then you need a different group. And the group that comes out of, say, Schrödinger's equation with the Coulomb potential. For those who know the math, I'll just tell you the symmetry group that you really want to use is O4 for this. So there's Kepler's laws. If you want the symmetry group of Kepler's laws, you use O4. Okay. So Parelomov took that work and then he said, oh, how about I can deal with any symmetry. So if you write a Hamiltonian and the Hamiltonian, the algebra is a Lie algebra, then he said, I can take any Lie algebra and define coherent states. There's a little bit of a sacrifice. So remember, in the harmonic oscillator, the wave packet of Schrödinger follows the classical motion, minimum uncertainty state, and doesn't change dispersion. If you replace the group, you can still demand the same criteria, but the uncertainty principle is more complicated if the commutator of the generators is not a constant. So you have to take that into account. And also that there's a limit. So Ehrenfeld, the limit to the time scale. So you say it follows classical motion for a limited time. Then Parelomov teaches us how to generalize the notion of coherent state. And so me in my heart, I feel like I'm a mathematician in my heart. I really like that. So when I was a postdoc, I thought I'm going to generalize what people do with oscillators following the Parelomov description to other symmetries. And then in Perelimoff's paper, he deals with SU2 and SU11, but he wrote a book published in the 1980s, which is really great, and he spells out how to construct coherent states for any Lie group. Okay, so this was my work at the time. So Milburn was my supervisor. Milburn wrote that paper about nonlinear evolution to turn a coherent state into a superposition. So I just followed Perelimoff's description. Oh, more there. But this paper here and over there, instead of the coherent state being a Gaussian, on the sphere it becomes a binomial distribution. And so you start off with a binomial distribution and then let it evolve. So I took Milburn's nonlinearity and let it evolve. And over here, this is a stereographic projection of the sphere. The coherent state as a binomial evolves into a superposition of two binomial distributions. So that's a superposition of two coherent states for spin. And the way to think about it is interesting. So if I pick up this water bottle and I give it imagine it's spinning. So if it's spinning clockwise, that's counterclockwise, spinning clockwise, then that would be one peak with the distribution of the spin, and then the other way is the other one. So that represents a superposition of spinning fast one way with spinning fast the other. So instead of this harmonic oscillator, it's a superposition of opposite fast spin. That's physically how to think about it. It's interesting to think that way. So now in quantum metrology, there's an effort, you see Wineland's name again, that Nobel Prize winner with Haroche. And so this paper came out in Physical Review A in 95. I was a referee for that paper, which I didn't say for almost 30 years, but now I feel enough time passed I can reveal. And so it was interesting to me when the paper came to Physical Review A. And this underlies a lot of quantum metrology, including efforts to improve clocks. They don't say that here. They talk about optimal frequency measurements. So it's not make the clock better, but make sure that you lock your clock to a good standard. This is the atomic clock area. And so they say in their paper that when we make an atomic clock, we have the atoms, and we use those as a reference. And if you want to double your precision of frequency, you quadruple the number of atoms. So there's a quadratic overhead. Okay, so double the number of atoms, double the precision, quadruple the number of atoms. But they said there's a way to go to linear that increase double the precision for double the number of atoms. And they said the way to do it, and they go through it there, is saying instead of each atom being independent, we'll make all atoms in the ground state with all atoms in the excited state, and that will give the advantage. And why that is, when I read it, I thought, okay, I get it. And so I'll tell you how I think about it. They go through their analysis. But if you have all atoms in ground, all atoms in excited, and you say the physics of every atom is the same, including the decoherence, then there's a permutational symmetry. So if you have a set of atoms and you reorder them, the physics doesn't change. Mathematically, there's something known as Schur-Weil duality. So that's the mathematical form. But what goes on is if you say there's a symmetry to it, then you replace, you can then say, I will think of it as a collective spin. So all atoms in the ground state is mathematically equivalent to spinning fast one direction. All atoms in the excited state is spinning fast the other direction. And then the interference effect, those fringes, have a spacing that's linear in the dimension of Hilbert space. That's how you pick up that quadratic advantage. So I didn't say in the referee report, but I thought about it. But essentially, this is exactly the same as what I did over here. It's just another physical realization. So that's why I got it quickly. So the idea of making a superposition of two spin states is actually underpinning a lot of the strategies in quantum metrology to get a quadratic advantage. So there's a nice way to think about it. So in our case, and I'm working with Andrea Morello's group at University of New South Wales, they're working with an antimony atom, Sb, in the periodic table. It's the isotope 123. And the antimony has the property, it's a spin 7/2 nucleus. So it's spin 7/2, 8-dimensional Hilbert space. So the nucleus is spinning, and the goal is here, let's put that single nucleus, not an ensemble, not a collection, but one identified nucleus, in a superposition of spinning fast, counterclockwise with clockwise. So that's the idea. And then when I was visiting the group, it's kind of what I was thinking about many years ago, and that nonlinear evolution comes into play. And then my mathematical way of thinking, I was able to help improve the control methods so that we could do things a lot faster before decoherence. And so the way it works is you can see that nucleus, in our case spin 7/2, and we want to make a superposition of clockwise and counterclockwise spin. And so that would become the cat state, not the oscillator, but the superposition of two spins. We need the nonlinearity, and the way to get the nonlinearity is to have some kind of field that distorts the nucleus. So if the nucleus is a ball, we need to be able to distort it and get a torsion effect. And so the way that works here, the antimony sits in a silicon substrate. So antimony has 5 outermost electrons, 4 bond to neighboring silicon, and the 5th electron we use to prepare and measure and remove it for the nonlinear evolution. And over here, so this is what you see, and this is a torsion. So by applying electric field, we can put some torsion, so basically stress the silicon, cause forces on the nucleus, and that gives us a nonlinear evolution. So that's the idea. So the nonlinear evolution on that spin system will take us from a spin state to a superposition of opposite spin states. That's the theory. The effect of the nonlinearity, if you look at the spectrum, nonlinear spectrum allows us to have different spacing between energy levels. There's 8 energy levels for a spin 7/2 nucleus, and by making nonlinear spacing, we can use different microwave fields to drive different transitions. And then the way it works is that we have that red dot is the antimony that we identify, the nucleus. The electric field here causes the torsion on the nucleus, so that chooses the strength of the nonlinearity. The microwave field directly drives the nuclear state, so with the microwave we're able to drive transitions. And the upper part, the SET, is a single electron transistor, and so when we reattach the electron, so we have an electron there, we use the electron in EPR, electron paramagnetic resonance, write the nuclear state we want to start with, rip off that electron, microwave field controls the nucleus, the electric field controls the nonlinearity, then we reattach the electron to read the state, and then the electron goes to a single electron transistor. If it's spin up or down, it's read differently. So there's a lot going on. These are well-developed techniques, but complicated. And then this is the experimental paper, where here, that's the antimony nucleus. This is a nanograph image of the experiment, exactly like I showed you on the previous slide, but that's what's built. The nonlinear evolution, and then these, okay, I mentioned Wigner functions before, just to warn you that there's no good Wigner function for spin, but there's compromises you can do. So it's a kind of Wigner function for spin. So you can see North Pole, South Pole, and then this is the hammer projection. So the above, the gray is mirrors. You can look at the back, and a hammer projection comes from the 1860s. If you look at a map of the world, you only see one side, but the hammer projection allows you to see the whole world as an ellipse. And so by the hammer projection, we have the North Pole, the South Pole, and then you see like 1, 2, 3, 4, 5, 6, whatever, 1, 2, 3, 4, 5, 6, 7, probably 8. There should be like 8 blues here, which would correspond to the interference fringes that equal the dimension of the Hilbert space. And so these are all experimental results. So we prepare the cat state, the superposition of two spins, and by eliminating some of the frequencies, we're able to restrict to a subspace. So we're able to study the spin half, the spin 5 halves, I think, and the spin 7 halves. and the hammer projections show what's going on. So we're able to prepare coherent states, we're able to manipulate them, and everything we do is like 99% agreement with the theory. So we're really able to play with this system and do everything we want. So that produces the superposition. The right side is essentially telling you our techniques for preparing the coherent state to start with. And then here, I think that's the last slide. No? Okay. These are the technical details, but I think what I'll do is just go back to, I'll go back. I'll just leave it on this, and I'll just say, like, there's a lot of technical details on how we sped things up, how we made sure things were coherent. This is just capturing all the experimental results. But the message to you, the closing message is, we're able to do with spin what 15 years ago was done with oscillation. And then the profit side is, in quantum computing, most of the stuff that's done is binary, zeros and ones, but computing can work with higher bases, base 3, base 4, base 5. This would be base 8. And so this is the start of a path towards doing quantum computing beyond base 2 to a higher base. So that's the profit story. That's it. Thanks.